right. Yeah, we're running along. Yeah. Okay, so next section, and this is the final section, right?
Yeah.
Three sections. Did you want to take it? So we can speed up a little bit. I'll let you go ahead and take it so we can. All right.
Dan talks more than I do.
You're very welcome.
You still got it.
Okay, so we're basically going to talk about connectors and then a little bit about some of the measuring tools. The most common connector that we use is called a PL259, which is the male part of the connector. The female is an SO239. The PL stands for plug. The SO stands for socket. They call them UHF connectors, but they're really VHF and below. They're not very well suited at UHF frequencies. Normally you would use a type N connector when you're looking at UHF, the higher UHF. They also have the advantage of being, I'd say, moisture resistant. I think in the ARL definitions, they call them waterproof. I don't actually believe that, but they do seal, so they are more water resistant. They also cost a factor of 8 to 10 times as much as a PL259. So you use them when you have to. And unless you got a lot of money, you stick with PL259s.
Almost every antenna you buy for VHF, UHF is going to be terminated with
an SO239 probably. A lot of times you'll see BNC connectors, which is a bayonet type. It's a quick connect, disconnect. It pushes on and twists and locks. You see them on test equipment, oscilloscopes, signal generators, things like that. So that's where you would normally use it in a ham shack, is connecting up to that type of equipment. Some of the smaller, like QRP radios, will tend to have BNC connectors on them, the low power ones. There's an SMA, which I can't remember what the SMA stands for anymore, but it's a very high frequency connector, probably the highest frequency of all the ones we're going to talk about. It's good up into the many gigahertz. They're about 1/4 of an inch in diameter. That's what you'll find on your handheld radios. In most cases, it's going to be a normal SMA connector or a reverse SMA connector. The Baofeng uses a reverse. ICOM and Kenwood use a standard SMA type connector for their antenna.
So and what's our reverse SMA?
Say that again.
What's our reverse SMA?
Oh, it's how do I describe it? In a normal SMA, the female side is threaded externally. The male side has internal threads and a pin and screws onto the female part of the other half of the connector. In a reverse SMA, it has internal threads and still a socket, right? What's your Baofeng?
Well, the Baofeng has the female on the radio rather than on the antenna.
Yeah, it's got internal threads and a male pin on the radio. Whereas if it was a normal SMA, it would have external threads and a socket. So that's why they call it reverse SMA.
And what's the big difference? Why couldn't they just use standard SMA?
That's a very good question. You'll have to ask the Chinese. There's a lot of things that would be nice in this world if they were standardized, but people tend to think I know better or whatever reason and do things differently. So,
And SMA stands for subminiature type A. We find these where I work, we find these in the final transmitter stages of pulse type equipment, which would be transponders and DMEs, that type of stuff.
if you look inside of a typical ham radio base station radio, you'll see internal connections in there made with small coaxial cable with SMA connectors on it to connect different parts of the radio together. As I mentioned, the type N, which is really a UHF. It's good up to, I think, a few gigahertz. But the downside is they're quite expensive and different set of tools to do those as opposed to a PL259. And 259 is the most common you're going to see almost everywhere, even though they do call it UHF. It's not. This shows, and these are not to scale, actually, because an SMA isn't that big compared to an N. The N connector is physically about the same size as your PL259 down here. And you see it's in the chart, it's showing it in the under a 1 gigahertz range, in slightly above 300, somewhere in that range. There's lots of variations of this. MCX is something, if you look inside of a laptop computer, that's normally how they make connections to the antenna for the wireless antenna that's built in. This is way out of scale. These things are very, very small. They're very hard to snap on and take off without bending them. There's different types of SMAs. There's an SMC, which is slightly different than the standard SMA, but the only ones that we really need to deal with are the PL259, the type N, BNCs over here in the middle. You can see it's a quick disconnect type, and SMA. I don't think there's anything else on the test questions. And you're unlikely to run into most of these other ones. So which of the following is true of PL259 connectors?
Oh,
Commonly used at HF and VHF. Which of the following RF connector types is most suitable for frequencies above 400 megahertz?
Bravo.
Bravo. Yeah, we didn't talk about a DB25. That's a computer type or serial communications. It's old printer port connector, 25 pin D connector. Don't see those much anymore. Some people have trouble installing coaxial cable connectors. It kind of depends on your expertise and the tools you're trying to use. If it's a solder type of a PL259 connector, all you need is a soldering iron and a sharp knife and practice. In most cases, people have gone to the crimp type connector where you crimp the outer shield. It's much easier to install, but it does require buying a crimping tool. And in those most of those, you still have to solder the center connector, but that's pretty simple. It's just a wire coming through the center of it, and you cut it to length and solder it. You definitely want to make sure that you've got a good crimp, so that you have a good connection with the shield, and you have a good solder joint on the center connector, because those can both cause a lot of problems if you don't have a good connection at that point. It causes some of the stuff we talked about before. Change in the SWR because of mismatch through the connector. If your connector isn't, and they can loosen over time, you really have to almost get some connector pliers to put them on with enough torque where they stay in place, or keep checking them, because they will tend outside with vibration, wind blowing the cables. They will tend to work themselves loose. What can cause erratic changes in SWR?
Bravo.
Bravo. Okay. SWR is short for standing wave ratio. And for one thing, it's a measure of how well your system is matched. Okay, your transmitter matched to the antenna. In most cases, if you're using a normal transmitter that's 50 ohms and you have 50 ohm coax, you have a good match up to the antenna, and that's where your mismatch is probably going to occur, because in most cases, your antenna is not going to be exactly 50 ohms, particularly not at a wide range of frequencies. It's going to be frequency dependent. You're only going to get the maximum power transfer when you have a 50 ohm source and a 50 ohm load. And you're losing half of your power on the source, and hopefully the other half's going to the antenna. And that's the best you're going to do. Any other combination, you wind up with less power actually at the antenna. And when you do have it matched as a 50 ohms on both ends, your SWR is going to be 1-to-1, which means basically that your forward power, which we measure as the power going to the antenna, is 100%, and there's zero power being reflected back.
Is it possible to get 1-to-1?
Yes, it's possible to get 1-to-1. Dan has claims he has 1-to-1 on his little
28.6.
at a specific frequency,
No.
and he's
1.1-to-1. Did I say 1-to-1?
oh, okay.
Yeah,
1.1.
1.1-to-1.
Yeah, which is for all practical purposes 1-to-1. Normally, if you're less than 1.5-to-1, you can operate without having to do anything. You're going to lose some power due to the mismatch, but you're not going to hurt anything. Most of the modern transceivers have circuitry built in, and they monitor basically reflected power coming back and forward power going out. And they will start decreasing power output when your SWR gets to 3 and higher, because it could damage the out. And if it's a transistorized radio, which almost all modern radios are, it can damage the power transistors if your SWR gets up in the 3-4 range. So they will automatically start to reduce power, depending on how bad the SWR is. I mean, it may get down to 1 watt, but you'll save $1,000 or $2,000 radio. These are the formulas that you don't need to know, just to kind of show you Uh, it's really, in one case, it's the ratio of the maximum to the minimum voltage you see on the line, or the maximum to minimum current, or also the impedance of the load versus the source. So Z0 in most cases is going to be 50 ohms. So if your antenna, which is the load, say was 75 ohms, then you're going to have a 1.5 to 1 SWR. And I did some sample calculations just to show what the different ratios.
What is an ohm again?
What is what?
What's an ohm again?
An ohm?
That's what he asked.
An ohm is the unit of measure of resistance or impedance. And you can see if we have the load being a lower resistance than the source, okay, like 33 ohms, it's still a 1.5 to 1 SWR because you're going to get the same kind of reflected wave coming back, regardless of whether it's higher or lower.
So absolute value.
The magnitude, yes. So what is standing wave ratio?
That would be alpha.
Right. How well the load is matched to the transmission line. If it was 1 to 1, it's perfectly matched. If it's something other than 1 to 1, it's not matched as well. So what reading on an SWR meter indicates a perfect impedance match between the antenna and the feed line?
Charlie.
What does an SWR reading of 4 to 1 indicate?
D.
Delta.
Yeah, a very bad match. So, it kind of follows the SWR is low when you have a good impedance match, something where you're close to 50 ohms, either above or below. It's obviously high the farther apart those two impedances are. When the SWR is low, you're going to have a little less signal loss because you have less reflected power coming back. So if it's not a perfect match, your forward power is going to be less than 100%. And the difference will be reflected power. So if you have 100 watts coming out of your transmitter and you're only getting 80 watts forward power, means you got 20 watts coming reflected back to the transmitter. So you only get 80 watts to the antenna. Now, it's not all lost because the 20 watts coming back gets reflected by the transmitter again and goes back up the line to the antenna. So you get some of it back to the antenna. And because you have a mismatch, part of that gets reflected back until there's none left to go one way or the other. Now, the downside is every time it travels from one end to the other, there's loss in the cable, which gets converted to heat. So part of that reflected power coming back is, if it was 20 watts, it's not 20 watts by the time it gets back to the transmitter. It's something less depending on the loss in the cable. And it gets reflected back. It's going to lose some more on its way to the antenna. So every time it travels back and forth, you get a little more heating in the cable. If you had a bad enough situation where you have very high SWR and you're getting half of your power going back and forth, you're going to get a lot of heating in the cable and loss, and it's not going to the antenna. At least a big portion of it isn't. This is a picture showing kind of the difference between your original signal, which is your forward power going out, the reflection coming back, and you see it's slightly out of phase, and what we call the standing wave, which is the addition of those two waveforms out of phase. And if you look at that with an oscilloscope or something, you will actually see that standing wave stationary on the transmission line. So what is the benefit of a low SWR? Bravo, sounds good. What happens to power lost in a transmission line?
Carly?
Charlie. As I said, most of the modern radios will automatically reduce power when you get over 3:1 SWR, basically to protect the output final transistors. They don't like the high voltage or high currents that you can get due to standing wave. Tubes are much more tolerant. You didn't have to worry about as good a match with a tube type radio, or at least tube type power amplifier. And they look cool. They glow.
Little romantic light while you're trying to talk on the radio.
Why do most modern solid state transceivers reduce output power as SWR increases above a certain level? Did we hear an alpha? When choosing an SWR meter, be sure that you pick one that operates over the frequency range you're intending to use. If you're going to be operating on VHF and UHF, you don't want one that only works on HF. The maximum power level is also important. Sometimes they will be limited to, I mean, you can get small ones for QRP stuff that maybe do 10 watts, sometimes 20. And if you had a normal base station, most of those will put out 100 watts typically, at least at HF. You may not get 100 watts on VHF and UHF. You may be limited to 50 or 75, depending on the radio. But you still need to make sure that it'll handle the power you're trying to measure. And obviously, if you had a power amplifier that was, 500 watts or 1500 watts, you definitely need a bigger watt meter and a more expensive one. And obviously, you not only can get erroneous readings, you probably damage the instrument. You only read stuff once. And some of the, and actually, I would say a majority of the watt meters allow you to measure both forward and reverse power. In some cases, they will indicate SWR.
2 meters and 70, and this one here is for Jeff. So
There's a couple examples of a digital SWR watt meter, which is nice and easy to read. and it shows you forward and reflected power and SWR. They usually cost a little bit more than the analog, but they're definitely easier to read. The one I'm showing here is both HF and VHF UHF, but you have to flip the switch. It's not automatic. And of course, you got 4 sets of connectors on the back of it. The one on the right is what we call a cross needle, and there's actually 2 meters. Each one has a separate needle. One is indicating forward power, one is indicating reflected power or reverse. And there's a scale which I find very hard to read. I have one of these. These markings show you the SWR. So where the needles cross, whatever line that is the SWR reading. In the case the one I have to really get close to it. Let's see. I also have one like this, and I can see that anywhere.
Oh.
The cross needle one was a donation. I didn't have to buy it.
That's the best one.
That's the best kind. It handles, the other one only goes up to 100 watts. That cross needle one will do a kilowatt, I think. Which of the following should be considered when selecting an accessory SWR meter?
Delta.
I heard an alpha, a delta. Got any Bravos? Any Charlies?
Oh,
Well, let's go with alpha.
okay.
The modulation doesn't affect SWR, and the distance the meter located from the antenna technically changes or will affect the SWR reading because of loss in the cable. So if you're reading SWR at the transmitter, okay, the reflected power coming back is smaller because you lost some in the cable coming back to cable loss. So if you
So where should you have your meter?
put the meter up at the antenna end, you'd probably see a higher SWR than you would back at the receiver end.
Hmm.
But that's not a consideration for buying the meter. It's just where you put it. You can also measure SWR with a directional watt meter, and that's kind of what we've been talking about, where it's the ratio of forward and reflected power. If it doesn't have like the cross needle one where it has the markings and you're only seeing forward and reverse, you can calculate it just by taking those 2 measurements. And you use this simple formula I've shown, which is actually a lot simpler than it looks, but it's very easy to plug in. You're taking the ratio of reflected over forward power, and it's 1 plus the square root of that ratio divided by 1 minus the square root of that ratio. So it's a simple plug-in, easy to do. It just looks intimidating. It's not on the exam. Which instrument can be used to determine SWR?
Delta.
The iambic pentameter is poetry or something like that, as I recall from 70 years ago. Where should an RF power meter be installed?
Alpha.
Alpha. So in the feed line, it would be better if you could do it at the antenna, but that's not always practical. Especially if it's on a tower, unless you had some way to remote it. Okay. There's things called antenna analyzers. And I brought one along, which after this we can maybe show a couple of these things. And it will measure SWR, and usually most of them will allow you, or the more expensive ones, to actually plot out a little graph as it scans over a frequency range. Some of the cheaper ones will just measure, let you change the frequency, but they'll show you what the SWR is at the frequency as you change it. It doesn't graph it. You're going to get the lowest SWR at the resonant frequency of the antenna. Because if you recall from when we talked about resonance the other day, I guess it was last week, it's when the reactive components cancel each other out, so you just have pure resistance. So when it's resonant, all you see is the series resistance of the wire in the antenna and another resistance we call radiation resistance, which is a measure of how, well, they didn't see the video, how well your antenna is coupled to the multiverse, which happens to be, if I recall, 377 ohms is the characteristic impedance of free space. So your antenna is trying to make that match. And there's gets long and complicated what the radiation resistance is. But when you see your antenna, if it happened to look like 50 ohms and you had very, very low resistance in the antenna, it was heavy gauge copper, that 50 ohms is going to be the radiation resistance. Some of these analyzers will also let you measure the reactances, either capacitive or inductive. In some cases, they'll even let you show it as a Smith chart, which technicians don't get the fun of Smith charts. I always like Smith charts. They're kind of neat. Also, you can use it as a signal generator, and that's how it works to do some of these other measurements. It actually generates a signal down in the, few milliwatts, maybe 10, something like that, and measures the through and reflected signals. So it'll do a lot more things than just a standard SWR meter or a typical antenna analyzer. I think Dan and I both brought a nano VNAs, which is a very small, cheap. Everybody should have one. They're only about 80 or 90 bucks.
Yeah, I got the original version, the H, not the H4, and I think it was $60.
Okay. I think I paid about 80. Mine's an H4.
Yeah.
But they will do all kinds of stuff where actually some of the more expensive, like the one I brought, which doesn't belong to me, a rig expert, about $400 or $500, and it doesn't do nearly as much. But it helps support Ukraine because that's where they're made. On the left is a popular MFJ one, which really is kind of meter readouts and this little LCD display, which shows you some stuff, but it doesn't graph it. On the right-hand side is a nano VNA, but I don't know what version that is, and there's several. they're all based on the same basic design, but like most things that come out of China, they sell them under a lot of different names, and usually you get back up a set of connectors and adapters. You have to calibrate it, so you get these. One is an open, one is a short, and one is a 50 ohm load. So you go through those 3 steps, and actually what you're doing is you're calibrating it on 3 points of the Smith chart. Because I like Smith chart. Which of the following is used to determine if an antenna is resonant at the desired operating frequency?
Bravo.
Bravo sounds good compared to the choices. Oh, let's see. Does anybody know what a VTVM is?
I do. Hard to find these days, but I know what it is.
I should dig mine out. I got it in the storage unit. It's a vacuum tube voltmeter.
And it's called for in almost every maintenance manual in my maintenance manual library at work, but yeah.
Yeah.
We all use digital voltmeters
Yeah.
now.
I was with a customer that had one of those last week.
Oh, yeah?
He does all the old electronic and stuff. And he had one, it's in a big case.
Yeah.
If an antenna's impedance is not 50 ohms, the impedance at the transmitter end of the feed line will not be 50 ohms. Even though you've got a 50 ohm transmitter and a 50 ohm transmission line, if you don't have 50 ohms at the other end, you're going to see something other than 50 ohms. So you use, and I hate this, they still call these antenna tuners. They do not tune your antenna. Your antenna, when you tune it, you're changing the length of the elements to get it resonant or close to resonant at the frequency that you want. When you use this antenna tuner, which is really a matching device, you're trying to correct the impedance that the transmitter sees. So instead of it being 3-to-1, which it would be at the antenna, when you do the quote antenna tuner, you could probably make it look like 1-to-1. It's still 3-to-1 up there on the other side, but as far as your transmitter is concerned, it's fat and happy, and I'm transmitting into 50 ohms. This is a little QRP type. Usually these handle like 10 watts, and they're very small and portable, and that's how you would, tune up one of these little antennas like Dan has if you were out in the field and it wasn't pre-tuned.
XMRT.
I only heard the XMRT part. Are you referring to the BNC connector on the bottom here?
Yeah.
That's from it where you connect the transmitter to it,
XMTR is transmitting.
and you connect your antenna over here. So it's in the line between your transmitter and your antenna. And all it's doing, these 2 knobs over here are, excuse me, rotating a variable capacitor. And this one over here is changing values of an inductor, usually with taps on it. It's selecting different amounts of inductance. And they're normally configured as what we call a pi network. So you're going to have this inductor on each side of it. I don't draw it too well. Dan didn't do much better. So you have these 3 variables. So one of these, and the antenna one would normally be this side. The transmitter would be this side, and then your inductor is in middle. So you play with those to get the lowest SWR or match that you can get. And you make your transmitter happy.
So does it stay permanently attached, or is it just like temporarily for quote unquote tuning?
Oh, you would use it while you're actually transmitting. In other words, you set up the match so you're matching the transmitter to what it thinks is 50 ohms, or trying to. You may not actually get that close, but the goal is to try to make it think it's transmitting into 50 ohms. Now it does have a switch. This one has a switch so that you can bypass it and go straight through.
My
That's
head
good.
hurts.
Not sure. Haven't done much QRP why you would use that. So what's the major function of an antenna tuner or coupler? I hear-
Alpha,
I heard some alphas.
yeah,
You're matching the antenna to the transceiver. Not tuning it, matching it. Okay. Another thing that comes in very handy is called a dummy load. It basically allows you to simulate having an antenna hooked up so that you could test or tune up your system without actually transmitting. So even without a license, you could hook up your radio into a dummy load. Of course, in most cases, you can't transmit very long because this particular one shown says 300 watts. If you look on the back of it, it probably tells you for how many seconds you can do 300 watts.
okay.
You can imagine how much fun sailors would have with that name. That was the nickname given to people who you can pump as much information into as you want, but nothing intelligent ever comes out.
And you notice on this one, the title is a dry dummy load. I think that's because some of the older ones, there used to be a Heathkit cantenna, which was in a gallon bucket filled with transformer oil and resistors in it, and it would handle up to about a kilowatt for a fairly long time. That was not dry. And you had to replenish the oil because it would tend to leak and get messy. And so what's the primary purpose of a dummy load?
Alpha.
Alpha. What does a dummy load consist of? Ooh, I think I skipped that
Brother.
part.
Mhm.
Well, everybody got it right.
Yeah, they must have read it.
In
the heat sink.
Sometimes it won't be a passive, and they'll have a fan, but of course you have to have a power source, but they'll usually operate a lot longer than just a passive one.
And a non-inductive resistor is key. You don't want to wire around resistor
Right.
because it would have an inductance.
Right.
filter.
It doesn't want to look like it's inductive or capacitive. It wants to be pure resistance, which is actually impossible in the real world, but you want to get very close. Okay, so we learned what connectors, basically PL259s and type Ns. That SWR was a measure of the load matched to the transmission line or the transmitter. loose connections could cause a high or erratic SWR. An SWR of 1 to 1 would be a perfect match, which you probably never actually see, but you might get 1.1 to 1 or 1.05 to 1 if you're really good.
It's challenging.
Well, my 7300 with an auto tuner inside would go to 1.1 to 1 as far as the transmitter is concerned. But then an SWR meter connected between that and the antenna would show a much higher SWR. So a high SWR not only is a bad match, but it's going to create additional heating in the transmission line because of the reflected power going back and forth, and every time it travels, it's going to heat up the transmission line a little bit, depending on the amount of loss. Now, if you had very low loss transmission line, it's not a big factor. If you were trying to use RG58 at UHF and you had 100 feet of it, make a big difference. You'd probably not get any signal at all because of if you had a mismatch. Let's see, we measure SWR with a SWR meter or a directional watt meter. You need to make sure that you've got a meter that handles the frequency range and the power levels that you're talking about or you're wanting to measure. If it's a directional watt meter, it normally shows you forward and reflected power. Most of them today are a combination, and they do SWR and forward and reflected. An antenna analyzer, which is specifically designed to do SWR, maybe a little reactance, but they don't do a lot of the other things that you can do with a vector network analyzer like the Nano VNA. Antenna tuners are matching devices, not tuners, and they only match the antenna to the transmitter. And you can use a dummy load to avoid transmitting and for test purposes, but it needs to be a non-inductive resistor in some way to dissipate the heat, either on a heat sink, or like the case of the old Heathkit one in a bucket of oil or something like that.
So, when you talk about the heat, builds up the heat, what happens?